This podcast is sponsored by the Norwegian Geotechnical Institute, NGI, your expert partner for offshore wind.
Hi, my name is Rasmus. I'm a geotechnical engineer. Back when I was a student, I wanted to build bridges. I guess, like all engineers. But then I discovered wind turbines. Today, I'm a specialist in the design of the foundations that support offshore wind turbines. No days are similar, because making the optimal foundation design requires the consideration of many different components. If you're listening to this, then you're probably, like me, fascinated by these massive engines of renewable energy. You might even be fascinated about how you can build a wind turbine that reaches almost 300 meters up in the air. Or you might just be fascinated by the global transition to clean energy that we'll all experience in the near future. That is what this show is about. Here, I'll be speaking to some of the world's leading experts about the history and science behind calculating and building wind turbine foundations. And of course, about how these foundations interact with the wind turbines above. So, get ready to hear what the best experts have to offer when speaking about big cylindrical open-ended steel pipes called monopiles and cylindrical steel buckets installed with suction called suction buckets. In this episode, I will be speaking with a colleague of mine, a colleague who has been deeply involved with the development of the suction bucket foundation. His name is Per Sparrevik, and he works at NGI, the Norwegian Geotechnical Institute. And let's have Per himself explain what a suction bucket is.
A suction caisson, or a suction anchor, a suction pile, it has many names. A bucket foundation consists of a cylinder with a closed top. On the top there is an inlet for pumping out water and evacuate air, etc. when you lower this caisson through the splash zone. And when you install this caisson into the seabed, you pump out the entrapped water after the tip of the caisson has penetrated by weight into the seabed. You then have a sealed confined void, and you pump out water from this void. When you are pumping out the water, you will get suction pressure, under pressure. The under pressure is controlled by the weight of the caisson, but mainly by the penetration resistance. This is simply Newton's third law about action and reaction. So except for some maybe rate effect on the penetration resistance, you cannot control the suction pressure generated inside this void. It is controlled by the resistance in the soil. Then in clay, it is more or less straightforward, but in sand, something happens with the soil when you pump out water. You create a steady state seepage around the skirt walls, which reduce or almost give you zero effective stresses. You could say you more or less create quicksand, and that will reduce your penetration resistance significantly, almost by 90%, especially at the skirt tip. So that means that you need less suction. And once you turn off the pump, you have immediate pressure equalization, and the conditions return to with no to normal conditions. When you close the top of this caisson, you suddenly increase your holding capacity significantly, because then you have another situation. You don't only rely on side friction, etc. You have the complete cross section of this caisson, which is closed, which is holding you in place. And in many cases, it is actually the weight of the water above the caisson which is holding it in place. So that is, in short, the principle of a suction caisson.
The installation of the suction bucket is less noisy when compared to that of a monopile. And the noise issue is actually quite important, and we'll touch upon why a bit later in this episode. The suction bucket is also an interesting concept, as it was actually developed for oil and gas platforms, but its use has now transferred to offshore wind. But let's have Per Sparrevik tell us the history of the suction bucket foundation concept.
Suction anchors or suction caissons has quite a long history already. Back in the late 50s, there were different concepts. Those were pretty strange because the shape of those anchors were different, and also the holding capacity was derived from active suction. Actually, they had pumps pumping out water from the embedded object all the time to create a steady state suction. Those anchors were called hydrostatic anchors as well. Then also Shell did some installation at the Gorm field, but really the start of the modern suction anchor, I would say, was in conjunction with a offshore test for the Gullfaks Sea gravity-based platform. This platform is equipped with the 22-meter long or deep concrete skirts, and the issue was, could those be penetrated into the seabed at site? And then on short notice, Equinor and NGI and other contractors put this test together, and there was a dummy piece of the thick concrete skirt with the instruments, like a CBT, you could say, and we had to drive that test piece 22-meter into the seabed. And then the idea came up to use suction caissons, two twin caissons, to drive it down with the under pressure. At that time, it was just a tool to check the penetration resistance of this piece of this concrete panel, and no one really thought of the future use of the concept. Obviously, it took some time, and I know that Turinge Kjelta at Equinor had it in mind, but it was like 5 or 6 years later when this concept started to grow again, and Equinor had 2 jackets in plan in dense sand where they wanted to try this out. And that was when I came into the picture with this paper in 1991. And from there on, it was just rolling on.
Here, Per is speaking about Tor Inge Kjelta, another geotechnical engineer who today is heavily involved in the offshore wind development for Equinor, a Norwegian energy company. Back then, Equinor was called Statoil, and they exclusively worked with oil and gas. And Tor Inge Kjelta was working on the development of one of their drilling platforms. But today, Statoil have changed their name to Equinor, and they have also turned towards the development and building of offshore wind. But back to Per and the results of the first offshore tests, where NGI was contracted by Statoil or Equinor to help with the testing. And these were, by the way, quite successful.
Yes, it was successful, even more successful than people thought of at that time, we could prove that it was possible to penetrate the deep skirts of the Gullfaks Sea platform, and also the suction driving was successful also really at that time, because this was new and there were mitigation methods integrated in this twin cylinder structure, like water injection. Also cyclic penetrations were performed, but really that was just to make sure that this uh, concrete test panel could be installed to the target depth. Now, maybe 20 or 30 years later, those mitigation methods are hot again for the difficult soil conditions encountered in offshore wind.
The installation part of the suction bucket can be risky. If the installation fails, this can of course have a big financial impact. And therefore, it is important to have a backup plan. A plan with various solutions to mitigate anything that goes wrong, and to ensure that the suction bucket gets installed anyway. Many of the mitigation solutions used today are very similar to what was used for the first offshore test in the North Sea. Two of these are water injection at the skirt tip and cyclic installation, where the suction bucket is moved up and down by the pressure in the bucket. Of course, Per has done a lot of these offshore tests.
Now, this was in sand, and really also in 1991 there was a soil investigation in dense sand where Statoil Equinor planned to do those jacket installations. And in conjunction with the soil investigations, it was put together NGI and Fugro offshore model testing of installation and operation of suction anchors. We put a steel cylinder on the drill string on one soil investigation vessel, and then we could pump water out and close it through the drill string. And those tests were really an eye opening for everybody. To penetrate something in dense sand, the resistance, especially the tip resistance, is very high. I mean, you can hardly poke your finger through the seabed. And we had done calculations and expected that things should happen when you apply suction and you get the steady state seepage through the sand. That should reduce the effective stresses and thereby the penetration resistance. But I think no one really could imagine that the effect was that large. We virtually removed all the tip resistance. The total resistance is decreased by more than 90%. It's like a hot knife through butter. And the operation is stable. The risk for piping and other unstable conditions in the soil was low. We could repeat it many times. We could directly check the difference in penetration resistance with or without suction. And we also could do some pull-out test and get some preliminary results on the effect of rate. At that time, geotechnical conditions were more or less based in drained or undrained conditions, but really for those suction caissons in sand, the loading is in between, and the in between condition, partly drained, or in many cases because the load is short term, was a game changer. The capacity is just extremely high. In some cases, it is probably the water depth or the cavitation pressure, absolute vacuum, which is the limiting factor.
I find it very interesting that even today you meet people who don't believe that suction buckets can be installed in sand. If a suction bucket is pushed down into the sand, the soil resistance at the tip of the skirt will be very high, and it's therefore impossible to push it in. But what these offshore tests showed was that the suction introduces a flow of water from the outside to the inside of the bucket, and this flow reduces the effective stress at skirt tip. And the tip resistance is then reduced drastically. So these offshore tests in the 90s actually showed on a larger scale that installation in sand is possible, and that it is the water flow that makes it possible.
Yes, and after those field tests where the concept was demonstrated and really accepted this will work, model test in the lab followed in 93 and 94, and where we could more quantify effects in controlled conditions. And then they went ahead to design and install the first jacket with the caisson foundation. And that was really when also the name bucket foundation was invented. The name comes, it looks like an inverted bucket. And the first platform was the Draupner platform in the North Sea. And because it was a new concept, it was quite heavily instrumented. And half a year after installation, this platform was subjected to the famous Draupner monster wave. That was a wave with no trough, but a peak of almost 20 meter hitting the platform deck and really created a short-term huge overturning moment. And instantly, by the recorded data, we could see that the pull-out capacity was extremely high, and it was more or less undrained conditions. And probably, if the platform should have failed, been overturned, it wouldn't have been because of the foundations in the sand. It would have been yielding steel.
So if you don't know the famous Draupner wave, it was the first measured rogue wave with a maximum height of almost 26 meters. But I suggest that you do a bit of Googling to learn more about that big event. But what it did for the suction bucket concept was to act as a great test or demonstration of the holding capacity of the suction bucket in sand. The explanation as to why the holding capacity is so big can be found in the flow of water. In order to move the suction bucket out of the soil, you will have to drag water through the soil that is inside the bucket. And because of the sand's permeability and that the load is relatively short, there's no time for the water to flow through this sand block. The weight of the soil inside the suction bucket is therefore kept inside the bucket. And this adds a large extra weight that is then used to keep the foundation in the ground. So both installation and holding capacity were demonstrated to work well for suction bucket jackets in sand in the beginning of the 90s. After this, the industry stopped using the buckets. But why?
Yeah, the break was pretty natural because around 95, as it all started with the bottom fixed jackets, there weren't any more bottom fixed jackets due in the pipeline, and everything went into deep water. So that is actually the main reason why the fixed platform application stopped. But as you say, in deep water you need mooring anchors. So Equinor and also others turn directly to the mooring industry, and especially in deep water.
Suction buckets also work in clay because the tip resistance is small and therefore there's no need for the flow around the pile tip to penetrate the skirt. The pressure difference between inside and outside the bucket is sufficient to push the skirt into the ground. Soft clay profiles are often found when moving to deeper waters, so these installations in the late 90s were done in soft clay.
That was soft clay and the homogeneous condition. It really took off in the late 90s. There were a lot of installation for deep water moorings in Brazil. They started to use it in the Gulf of Mexico, and even in China it is used. And the interesting thing is nowadays I and others you receive questions and interest more or less from all over the world about those suction anchors, because it is quite a neat concept in itself and intriguing. When it comes to offshore wind, it was really in 2013 where we did some suction bucket penetration trials. We have to remember in offshore wind, the water depth is limited. That implies that you cannot rely on unlimited suction driving pressure because you will get vacuum, and the soil conditions are highly variable and sometimes difficult. But to make this concept robust, we need to investigate more, pushing the limits, going into more difficult soil conditions, see if we could install it.
What we have to remember is that the pressure difference between inside the bucket and outside is what drives the foundation down. The higher differential pressure, the higher the driving force. But there is a limit to how high the pressure difference can be. This is controlled by two factors. The first is the strength of the steel construction, and the second is cavitation of water. The steel construction is something you can take into account in your design. For example, you can increase the wall thickness, but cavitation is only controlled by the water height. That means that when you are at a deep installation, this is not a problem because the water level is high. But for an installation at shallow water depths, this needs to be considered. This is the case for many offshore wind development projects. And this is what Pierre was talking about when he mentioned the problem with vacuum, and one of the reasons why a series of trial installations were done. And as it was for the suction buckets in sand for oil and gas platforms, it was again Inge Chelta that was leading this development, but this time focused on the foundations for offshore wind turbines.
The first one with Equinor was initiated by Inge. The other one in 2014 was Fred Olsson. It was an offshore wind accelerator project from the Carbon Trust with Fred Olsson, and we tested both the monobucket concept from Universal Foundations and also a standard suction anchor as a reference.
Here, Pierre is referring to a carbon trust project that was carried out in a partnership with 4 large offshore wind developers: Equinor, Statkraft, E.ON, and Ørsted. This is again a good example of how the industry got together to transfer the methods known from oil and gas and make them more applicable for offshore wind. These trial installations were completed across a range of tricky soil conditions, including soft and hard clays and layered soil profiles, all reflecting typical soil conditions for an offshore wind farm. Many of the findings from these trial installations were used when Ørsted constructed the first offshore wind turbine that used suction buckets for the foundation, Borkum Riffgrund 1.
Yes, that was the first real application for the offshore wind industry. A lot was learned also there. One issue is, for example, that for those offshore wind sites, they are usually subjected to a lot of scour, and then it is economical to pre-install the filter layer, rock fill, for the scour protection. And obviously, we then need to penetrate those bucket foundations through the rock fill and continue suction. So it has been new elements for offshore wind for this concept. In the beginning, we thought we know it all from the oil and gas industry, but there are certainly more learnings, and we are continuously expanding the applications in soil conditions which earlier would have been considered as non-feasible for installation.
Different solutions exist when suction buckets are used as foundations for offshore wind turbines. There are two main systems. One where only one bucket is installed. This concept is very similar to a monopile, but the buckets here are wider and shorter than a traditional monopile foundation. The second solution is where the suction buckets are connected by a grid of steel rods to create one tower. This is called a jacket, and so far this solution is used for most installations. The concept with suction buckets and a jacket is frequently referred to as a suction bucket jacket, or simply just SBJ. This was also used for the wind turbine at Borkum Riffgrund 1 that was used as the demonstration project. But after that, in 2018, suction bucket jackets were installed in 2 offshore wind farms, more or less at the same time. The first one was in Scotland and is called Aberdeen Bay, and the other one is called Borkum Riffgrund 2. Do I have to say that Per was heavily involved in Borkum Riffgrund 2?
Yes, Borkum Riffgrund 2, where NGI and Framo was involved, that is Ørsted again, consisted of 20 suction bucket jackets, and up to now is the biggest industrial scale application. And the installation went smoothly. The concern in advance with small thin layers of silt and clay we never noticed. Usually when you go from CPT test and you identify different thin layers, when you go up to the large scale of penetrating caisson, you seldom notice it because you have those transition effects.
Actually, I was also involved in this project as well. I was present on the vessel for many of these installations. The work on a vessel is very different from the work when you are sitting in your office. You get a different view of the challenges involved in working on a floating construction site. Here, it's all about time and not about the last 2 digits in the calculations. These learnings have been important to me, and I think that helps me when I'm doing my daily design work. I definitely learned a bit about suction bucket installations. Sitting in the installation control room on the vessel for many of these installations, I've seen that the small oscillations we often see in a cone penetration test in sands, which indicate low permeable layers, did not affect the installation. This is just one example of the learnings that Per was talking about. Today, we have much more confidence when designing our installations, and we can also design suction buckets for ground conditions and soil types, which we previously considered not possible. All these learnings are important when a foundation concept for a given offshore wind farm is evaluated. The price is the main driver for a concept, and with better design models and site condition data, the better the estimate of the different foundation concepts. But how do suction bucket jackets compare with the very popular monopile?
Is that it is still a more expensive alternative compared to monopiles. And there are many reasons for that, but obviously the monopile is a simpler construction compared to a jacket. And the jacket construction facilities haven't been geared up on the more industrial production of many units. So there is a way to go there to optimize the construction. I doubt that a jacket ever can be cheaper than a monopile, but a monopile has its limitations when it comes to water depth and the size of the turbine. The limiting factor of the monopile is the stiffness. The taller it becomes, you will have problem with the resonance frequency. It is simply too soft.
Stiffness of the foundations is an important topic for offshore wind turbines because it has a direct influence on the resonant load from wind and waves. The interaction between loads and foundation is important. However, the rule of thumb is that when the response is getting too soft, that's when we get into problems. Jackets are a stiffer structure compared to monopiles, and therefore a better solution for deeper waters.
When it comes to the jackets, when the water depth is getting deeper, the turbines bigger, that is the time for the jacket concept. And then obviously, if you can gain more energy out of each turbine, the cost of the foundation can be more acceptable. So I don't think they ever can compete. It's just in what conditions can you use one concept, and in what conditions is the other more cost efficient. If the conditions are similar and you can use both, the monopile will be cheaper.
So, for soil conditions where both concepts can be used, it is clear that the monopile foundation is the preferred option. For special soil conditions and deeper waters, suction bucket jackets may be the go-to solution. But there's one more reason why suction buckets can be the preferred solution, and that is related to the noise during installation. The thing is that driving a monopile into the ground with a big hammer is very noisy, and compared to this, the installation of suction bucket jackets are close to noiseless. The difference is especially important for environmental reasons, to protect marine life, and in some countries, regulations decide the amount of noise allowed during construction. So it's not always just technical details that determine the type of foundation. There's of course price and regulations, and these are all evaluated before a project begins.
Yes, I agree. I mean, it's not fair to compare which one is the best, cheapest solution. They are based on very different principles. So you just have to evaluate for each site what is the benefit here, and then take it from there on. There are also obviously different concept. Can you use a monobucket concept? Should it be 3 legs or 4 legs? Obviously, for a monobucket concept, which is in one way the cheapest solution, you still end up with the limitations in the moment capacity. You are just simply standing on one foot. If you compare 3 to 4 buckets, we always say we prefer 3, because that makes static determined system. It's easier to know. You know that where the loads are going, and you know that you're not holding back anyone during installation. With 4 buckets, it's getting a little bit more complicated as you involve the effect of probably strains in the structure. It is static undetermined.
You know this problem from your daily life yourself. This is similar to a chair with 4 legs, and where the floor beneath the chair is not completely level. One of the legs does not touch the floor, and this makes the chair rock. This never happens for a 3-legged stool, because it only has 3 legs and it's statically determined. And this is exactly why it is preferred to make a 3-legged jacket. The 3 legs makes the installation much easier, and we always know where the force goes through the jacket. This is important because we use the suction buckets to control the inclination of the complete jacket. Here we use the 3-legged stool again as an example. If we take the stool to the beach, it is clear that if we want to sit on the stool without an inclination, it is necessary to push each of the legs into the sand with the correct amount of penetration. If one stool leg penetrates too deep, the stool will have an inclination to the side of that leg. This is the same for suction bucket jackets, where the penetration of each suction bucket determines the inclination of the complete jacket. So there's still room for improvements, and there's still a future for suction bucket jackets in offshore wind.
Yes, for sure. When you go into deeper water, and obviously the big question is, when is the optimal limit in water depth where you go from a bottom fixed platform to a floater. And I believe that in this gap there will be room for jacket structures if they are pre-piled or suction bucket jackets. That depends again on the soil conditions and the disturbance to the marine life.
We also have to remember that suction buckets are not only for jackets, but they can also be used as anchors for floating structures. They're already in use in the floating offshore wind farm, Hywind Scotland, and they're also considered for other new developments.
Yeah. Then we are back to the traditional moored suction anchor applications, and for Equinor's Hywind concept, suction anchors have been used, and also, I mean, you are really the main alternative here you compare with is a piled anchor, and that is more expensive to install. And the beauty with the suction anchor also is the symmetry. You can easily have several loading points and loading direction. There is no main direction which will give you higher capacity, which means that you can use a combined anchor with mooring lines to different floaters.
We got an interesting history from Per about the development of the suction bucket technology and how it was developed for oil and gas and later refined for offshore wind. And today, it's offshore wind that is driving the development of this concept. The risk of suction bucket installation is probably larger compared to monopiles, but they have advantages in noiseless installation, shallow penetration, and they work very nicely as multi-anchor solutions for offshore wind farms, which may be the next big thing. A big thank you to Per Sparrevik for joining me in this episode. You have been listening to Offshore Foundations, a geotechnical podcast about offshore wind turbine foundations. My name is Rasmus Klinkvort. Thank you for listening.
This podcast was brought to you by NGI, the Norwegian Geotechnical Institute, your expert partner for offshore wind.